Hi, and welcome to the second video in this series on how to use a BLE sniffer. In the first video, we went over how to use the TI-CC2540 BLE sniffer to scan and capture BLE advertisement packets. In this video, we will go over how to use the same sniffer to follow a connection and see the data being transferred between the central device and the peripheral device. If you haven't watched the first video in the series, it may be helpful to go over that video first before watching this one. I'll add the link in the description below to that video. As far as BLE sniffers, I see three main reasons for using BLE sniffers and three main uses for that. The first one being to debug problems with BLE connections that you're having between your central and peripheral device. Another one would be to reverse engineer a BLE device that you own. So if you have a BLE device and you want to figure out what the gap structure is and how things are working between the central and the peripheral device, you can use a BLE sniffer to try to understand that. And last but not least, it could be a very useful way of learning how the BLE works and understand how the data gets transferred between the central and the peripheral device. Now in my setup, I have a device called the lightbulb candle. This is what it looks like. I got this from Fry's for about $15. The device basically looks like a candle, has an LED that can light up in different colors and allows you to do some cool effects with the lighting, such as flashing, pulsating, candle effect, and some others. Now, the device has a companion app that's available on both iOS and Android and lets you control it from there. And we'll take a look at how this device works and the data gets transferred between the mobile app and the device itself. So first we launch the TI packet sniffer software and make sure you have a blank screen, a blank capture. Then we hit the play button, and I like to enable the automatic scrolling to see the packets come in real time. And now we can see the advertisement data that's being advertised by BLE devices in the vicinity. Now I'm going to launch the app for the lightbulb candle. This is what the app looks like. And as you can see, it detects a device. Sometimes it may be difficult to capture the connection on the first try. So in this case here, you can see something went wrong with the sniffer. So I'll restart the capture. And let's try to connect and see if we can detect a connection. So it may take multiple tries depending on which channel the connection happens on. And it can get pretty frustrating, honestly. Okay, so here we detected a connection, and we'll pause here in a second. But let me go over a couple of things that we can do with the lightbulb candle, and then look at the data that was transferred to accomplish these. So here I'm going to turn to a red light. I'll try green, blue, and then white. And then I'm going to disconnect. Okay. So let's pause the capture and look at the data. Okay, so once the sniffer captures the connection, it will stop sniffing the advertisement packets and switch to following the connection that it detected. So in this case, it'll switch from showing the green data to the yellow, which indicates data packets instead of advertising packets. So let's take a look at the last advertisement packet that was sent before the connection was made, which is the ADV connect request packet. And we have two addresses here, the init A and the advertisement A. The init A is the initiator's address, which indicates the address of the central device that is connecting, that sent this packet, and the advertisement address is the address of the peripheral device that the central is connecting to. LL data in this packet stands for link layer data, and that includes the access address, which will be used for the data packets during the connection, as you can see here. We have a CRC init value to be used for calculating the CRC. We have a window size, a window offset, an interval, latency, timeout, channel map, hop number, and SCA. SCA stands for, it basically is used for determining the worst case master sleep clock accuracy. And so in this case, you'll see these are the connection parameters that are being exchanged or relayed from the central device to the peripheral in order to be able to be synchronized when transferring the data. In the beginning of the connection, you'll see that there's a few data packets that are getting transferred between the central and the peripheral. One of them is a version, and that is to basically be able to detect whether the devices are compatible and can talk to each other. Other packets that are being sent include LL feature request, and that indicates what features of the link layer are supported by the central, and then a response indicating which of these is also supported by the peripheral device, which dictates what features can be used during this connection. Another data point that gets exchanged between the two is the MTU, and that is the maximum transmission unit, and that's to set the maximum data size being transferred between the devices in each packet based on what each device can handle. There's also and so in the beginning, when a master or a central device connects to a peripheral, it will go ahead and start discovering the services and characteristics of the peripheral device, and that gets accomplished by two or a few operations. One of them is the read by group type request, which will go ahead and discover what are the services, starting with the handle at 1 to the last handle consisting of 2 bytes, and the group type tells it what kind of service it's looking for. So when the master device actually starts discovering and looking for the different for these different services that the peripheral device has, it requests the handle, and the handle can be very helpful because it's 2 bytes long, and it's unique for this device, but it will reduce a lot of the data that's being transferred because it allows the central device to access certain characteristics via handles, which are 2 bytes instead of the UUIDs, which can be up to 16 bytes. So you'll see here there's a few operations back and forth between the master and the slave. So we have discovering services, and I won't go into too much detail in this. It is explained pretty well in the spec, but it usually happens on every connection. So if we want to skip past this data to look at more interesting data, and that is the data that writes to the characteristic, the request from the central device to write to the characteristic to change the light on the candle. You'll see that sometimes there's also read requests, and that's because the central device usually in some apps, sometimes in the scanner apps specifically, it will, after it discovers all the services and characteristics, it will actually request a read of all these characteristics so that it can display them to the user in the UI. So if we skip past these, we can see at some point it will request a write to a specific characteristic with a specific value. And because I've gone through this before and looked at the data, I know what to look for. It can be a bit overwhelming at first if you look at this data without knowing what kind of protocol or data flow happens. But here, for example, if we look at this write command, it is accessing an attribute that has a handle of 19 hex, and because it did the discovery before, it knows that this corresponds to UUID of a characteristic that indicates what light that is, or what color, changing the color of the light. In this case, I know this is actually the white color, so I probably missed a few of these rights. So let's try one thing, and this might help in kind of finding out where the right commands are versus looking at all this data that can be kind of overwhelming. But what you can do is go to the select fields, and under L2 cap packet, remove all of them except the ATT write command. And in this case, you'll see this was actually the last write that we did, which was the color white. I know that these bytes are white, are red, green, and blue, and the value indicates the intensity of the light, FF being the highest intensity. So if we go back up and look, we'll be able to see the other writes. So this was the blue. As we said, this is white, R, green, red, green, and blue. And we'll find that before that, there was the green write. It's right there. And the first one was the red. So here it is. So in this case, it wrote to this handle of 19 hex, the value FF being the second byte, and this indicated to turn on the red. The next one was the green. And then the last one was a blue, and the final one was the white. So this kind of helps you figure out, so if you don't know how this device works, when you run the application and you capture this sniff, you'll actually be able to tell what are the values that are being written to the characteristics, and give you a better understanding of how the device works in terms of which characteristics are being used for controlling the different operations of this device. If we look at the bottom, at the end, we'll see the last thing that happens is a terminate indicator that is being sent by the master, and that's when I disconnected from the peripheral device. So I hope you found this video useful. If so, please go ahead and hit the like button, share it with others who might find it interesting, and please add a comment below if you have any questions or have any suggestions on what you would like me to cover in another video. There are some other more interesting things with BLE that can be harder to sniff. That would include something like encryption. Obviously, there are more complex operations that might include multiple reads and writes and behavior that happens in the background on the device that we won't easily be able to tell from the sniffer. But this quick video should at least help you get started with understanding the different data packets that are being transferred between the central and the peripheral. Thank you, and hope you enjoyed this video.